Okay, so getting into approximating values, you'll see one of the things that happens here is when we're plugging in specific values, we get this undefined thing. And this usually happens when we're plugging this into calculators because, for example, we can't have a negative square root. So that's undefined. We can't figure out what that is. You can't take. We know that there's imaginary numbers, but for right now, we can't really have a square root. A normal calculator will not output imaginary numbers. Also, we can't divide by zero. A lot. I might have mentioned this before. I'm not sure if it was in an Algebra 1 video or this one, but let's say we have a group of three and it says, hey, divide this by zero. Make a group of zero. Well, I would just won't pick any. Well, that means you're not dividing by zero. It's impossible to divide by zero. There's more to it, but the very basics is that. So remember what division is. So, for example, if you have a group of six and it says divided by two, you're going to do it in groups of two, and that gives you six. So it's impossible to divide by zero. All right, so moving on. Others, as soon as this loads. Okay, other instances. Oh, wait, hold on. What are we doing here? Oh, so solving by a table, if you plug in all of your values, you'll see when our y values are the same. So when you have an x value and the y values match up, that means that's our solution. And that makes sense because think about it. If we recorded this value would be 4 comma 2, our input and our output. So then if we did this value, let me use a different color. This value, our input is still 4 and our output is still 2. So that's where they have to match up. So this is just solving systems of equations. We've done this in Algebra 1 before, but now we're going a little more in detail with different functions. So we also have to count parent graphs. Parent graphs are how we move things around. So for example, a parent graph is this. I don't know if we really looked at a radical, but a radical, think about it this way. The bigger the number gets, the smaller it gets. So like think about this. If you have 1 over 1, that's just 1. But let's say you have something like 1 over 10, that's smaller. And if you have 1 over 1,000, that's even smaller still. So that's why you end up getting these graphs. And eventually, the bigger a graph gets, you'll eventually get down to 0. So this right here, what's happening here is this is getting smaller and smaller and smaller. So if you have a bigger number, it's 1/2, it keeps getting, the y value keeps getting smaller and smaller and smaller. If you have a decimal, this becomes 2. It's essentially 1 divided by 1/2. So that's why anything that's a decimal here, you'll see all of a sudden it starts getting up really, really, really fast. And it's really hard to count these decimals because they're so small that it feels like they're growing really fast, even though it's not really growth. And in this case, if you have a really, really tiny decimal divided by 1, it's a really, really big number. You're essentially saying, like if you have 1 divided by 0.2, 0.2 goes into 1 5 times. So if you have 0.002, I said 0.1, 0.2. So if you have 0.02, this is going to go in there 50 times, and so on and so forth. So that's how come you get this weird shape. Now it's important to know the parent graph because what's happening here is our x is being subtracted by 3. That means this x is behaving like it's 3 in advance. So for example, if we have 1 over 2, it's just 1 over 2. But if we have 1 over 2 minus 3, this 2 is acting like it was way back over here. It's acting like over negative 1. So this 2 kind of starts moving over. It starts behaving like a different x value. So this, a lot of people think, oh, that means that they're going to start behaving back here, but it's not. It's actually going to make it move to the right 3. And then this plus 1, this is actually kind of happening to the x graph. So think of it this way. What's happening here is it's x minus 3, and then we're adding a 1 on top of the original function. So our input now is x minus 3, and we're adding 1, so the graph goes up. So this is going to go to the right 3 and up 1, which I'm sure Edmentum's going to beat me to that right now. Oh, I guess not. So it's just talking about transformations. And this one, our parent graph is that. So what's going to happen here is this is going to go to the right 3, and this x, this number right here, this coefficient, is this, we're multiplying this d. So we're going to multiply it by 2, so it's going to get a lot, it's going to grow a lot faster. And we'll get into those right now, I'd imagine. Let's see here. Oh my gosh. Okay, so here's our function f of x and g. So this is talking about those fractions, I believe, which I feel like, I think Edmentum doesn't realize that this is on a different slide. So what's happening here is, oh my gosh, Edmentum, you need to realize that you labeled these functions way over here. Or they might be their own functions. Let's assume they know what they're doing. I feel these criticisms of this learning program get a little too hard sometimes. So if we see here, this stays negative until it gets to 3. Nope, I think I was right. I think because this is 1 over x minus 3, and this one, I'm not sure. Are they stating the actual functions? They're not. Main idea is when we're looking at a table, we're still looking at this. All right, so pi isn't a regular number. It goes on forever. I honestly don't know. I honestly just call pi 3.14, but it does go on forever. Pi is basically this number of trying to connect a radius to an actual circle. That's how we get pi. And no one's like, there is no end to it. It just keeps going on forever and ever and ever. No one's I keep saying no one done it. It's not possible for it to end. It's just one of those weird numbers that exist in the world. So again, now we're comparing these. So all we're doing is we're doing an x and y table. We're plugging values in and solving for them. And this can actually be done on Desmos. So I'll bring this up later. So these are just graphs. I usually like explaining more, but I didn't realize that most of these are just, hey, here's the graph, here's the chart. Figure out where they connect. So let's get into an actual problem. So our job is to figure out where these numbers connect. We can do that with a chart by just keep plugging it in and keep doing it on forever. I don't know why they keep showing more of these. Let's get into an actual problem. All right, so again, we're doing our input. Oh, these are close enough. So here's the problem. When we're doing a chart, like how small are we going to do this? Like there has to be a point where we say that's close enough. And the reason why this works is, check this out. So right here, this is smaller than that, but all of a sudden, this is way bigger than that. So they had to have crossed somewhere. So we're going to guess it's about 1.5. And we're going to keep making these ratios smaller. We haven't found where they crossed yet, but we know that they're going to cross somewhere. So that's a pretty good approximation because we know that it's going to be bigger than 1.5, but smaller than 1.6, and we can still approximate more. So we're going to keep doing smaller and smaller numbers to try. Now we're doing it by 0.01. We're increasing by 0.01, and we still know that it's somewhere else. So we're going to keep making it even smaller than that. So that's what uh, Edmentum's trying to teach us is if we get to a certain point where a number becomes bigger than the other one. So, for example, if we're going like this is going 1, 2, 3, 4, and this other, I don't know what, we'll do random inputs. And this one's going like 0.33, and then all of a sudden it becomes 1, and then it becomes 3. This was a really bad example. Let's do this. 2, 4, 6, 8, and then this one becomes 9. It's like, wait a minute, something happened here between 6 and 3 because all of a sudden this one was bigger, but now this one's bigger. So then we're going to make whatever inputs we had get smaller. All right, so that's kind of the idea here. So they want us to find the solution using a table. So here's what I'm going to do here. So I'm going to use Desmos to do this. I don't know if, do they have graphing tools here? They have data plots, but I don't think they have graphing tools. Let me erase everything because I don't know where that thing came from. What you're going to do on Desmos is we're going to go to the actual, oops, give me a second, math tools. You can use matrices to solve it, although that's a very advanced way of doing it. So I'm just going to use a graphing calculator. And you guys are probably wondering, like, well, graphing calculator isn't the same thing, but you'll see what I'm about to do here. So what I'm going to do as soon as this loads, okay, perfect. So we need to do absolute value. So I'm going to type in abs. Usually this works, I think, because I did caps, I didn't understand it. Absolute value of 2x minus 1. I hate when it does that. That's the one thing I don't like about Desmos is when you tab out. So this is an absolute value. And what I can do here is hit this little gear and I can make a table. Cool. And then I can also input another function here to make this just as simple. So I'm going to do square root of, go back in here, x, and then I'm going to do plus 3. All right. So my goal is to try to make these match up. So time to go into my input. I'm going to make this a little bit bigger because we don't really care about the graph itself. We more care about how this is going to work. So if I look here, 3, 4, so all of a sudden this goes from undefined to 3. So we want to see when this crosses that. So I'm going to do, I'm going to delete all these. These are not helping me out right now. Move my 2 over here. 3. I'm going to delete this. So I see here that they crossed each other. Okay, so this is still on the lower end. But then all of a sudden, okay, so never mind. They still haven't crossed each other. So let me do 4. Okay, this is still lower. So I'm going to do 5. So it looks like this crosses, this is growing slower. So we definitely want to look at our negatives. So, no, that's not what I wanted. Let me try -1. Oh my gosh. Undefined. So let's try getting more negative. Let's try 10. I'm trying to find one where they're smaller. So if I try 3, this is still smaller. So I need to get even smaller than that. So I'll try 1. So that's bigger. 2. This is still bigger. And 3. Okay. So I think I lost what I was doing at first. So I see here that 2 is where I want to start off. So I do 2. All right, 3 is way too big. So what I'm going to do here is I'm going to try 2.5. I'm making it even smaller. Okay, so this is still smaller than this one. So we're good. 3, it kind of crossed it. So now I'm going to try 2.75. But we're getting a little closer. So let's try 2.8. Closer still. 2. Our goal basically is to not have this overshoot it. So 2.81 still hasn't overshot it yet. So 2.85. Oh, overshot it. So let's go to 2.84, 2.841, 2.842, 2.841, 425. We're getting really, really close. So, how many decimal places did they want us to do? So, find the solution using to the nearest hundredth. Well, hundredth is only 3 decimal places. So, I think that's going to be as close as we can get. Actually, hundredth is only, I'm sorry, hundredth is actually only 2 decimal places because it's tenths then hundredth. And if I go over, that's too far over, I think, because here we have a difference of like 0.012, and over here we have a difference of 0.005. So 2.84 is going to be our closest number. So that's how we use approximation by using a table. We look at which one starts off smaller, and then we get as close to we can without overshooting it. We can't overshoot it. In this case, they specified we wanted it to the hundredth place, so that's 2 decimal places. And you can see here, this is how they're doing it. They did exactly the same way I did it. Um, First, they started with integers, then they went to tenths. So they probably did a little bit better because I honestly forgot that we're doing it to the hundred. I didn't read it, to be honest. I'm just going to be honest with you guys. I didn't read it. So read your directions. So successive approximation. So the idea of successive approximation, hopefully this will load. There we go. So let's kind of get into this. So the approximation we did before was just kind of making it smaller, smaller, smaller. This one, first we have to determine the left side. So we got this. So we have these 2 functions. We have them separate. Now we're going to make them all over to one side. And we have this when we look at a graph. All right, so when we look at a graph, plug in the upper and lower bounds of the equation. So, bounds of the equation derived from step 2. So by doing this, what are we doing here? Oh, upper and lower bounds. I'm not sure what they mean by this. Plug in the answer upper and lower bounds derived in the. If a solution exists between the upper and lower bounds, one of the bounds yield a negative solution. So let me go back to step 2 because that's not making any sense to me. Rewrite this, figure out where it equals 0. Okay. Oh, we're trying to figure out what x value equals 0. Okay, so that's going to give us an answer. Look at the graph, and so we're using all kinds of tools here. This is a little strange, but we'll get into it a little bit more. Take the average of these bounds. So this is a weird way of approximating. It's much more involved than the other way of approximating. So I'm already not a fan. But advantages of successive approximation, process gets closer and more accurate. So this does get closer and more accurate, but honestly, with technology, it is a little better to do it. So solve the equation by approximate. So what is the approximate answer after iterations? I feel this is very subjective here, so I'm just gonna review the answer with you guys. So, first thing we have to do is we have to make it equal to 0. So if we plug in 2, this is 4, that's a negative, plug this in 0. So this would give us a negative. So our lower bound is 2 because that gives us negative. Our upper bound is 3. So we're using integers to kind of approximate this. Then we're plugging them in and subtracting them. Oh, this is just proving it. So we're plugging them in. And then we're going to find the average of our outputs. Or the average of, I'm sorry, the average of our two inputs. From here, what we're going to do is we plug in the average into there. Okay, from there, we're going to see is it an upper bound or a lower bound. All right, then we're going to find the average of that. So this is a negative. So this is our new lower bound. So basically what we're doing is we need to find where it's equal to 0. It's basically, think of it this way. This graph is crossing the x-axis. So we're finding the negatives and the positives, and we're just making it smaller and smaller and smaller until we get closer and closer to 0. So what's our new negative? What's our new positive? Oh, another positive? Oh, another negative, another negative. Oh, another positive. And eventually we get really, really, really close to 0. And the reason why this works is if they are equal to each other, then they should equal 0. So that's this idea of successive approximation. If these two y values are equal to each other, you should get 0. So you're just creating an upper bound, meaning the upper bound is where you got a positive answer, and the lower bound is where you got a negative answer. All right, so calculators using a table and using a successive approximation, which is that idea that we just did the plugging in values to get positives and negatives and then making new lower bounds by finding the average. And that's it. So I thought this was going to be a lot longer than it was, but it ended up not being so bad. I'm sorry I didn't really give approximation justice. I'm not a big fan of it. That's why I hardly ever cover it. But it is a pretty good strategy where you're just figuring out if it's a positive, then that's your upper bound. So you just do these functions equal to each other. If it's a positive, it's an upper bound. If it's a negative, it's your lower bound, and then you find the average, and then you figure out if it's a positive or negative. Ideally, you would eventually get 0, which would be your answer, but with these types of graphs, you're probably not going to get there. Hope that helps, guys, and I will see you in class.